We talk a lot about memory over there in computer land, running out of memory, accessing memory, cloud memory, storage, hard drives, data centers, all that. But what actually is memory? To explain, let me draw your attention to this scene from Zootopia. Here, Judy Hopps represents the CPU, or the central processing unit chip, that acts as the control center of the computer. The CPU is what handles all the computation, but if you want to store data for retrieval later, then that CPU has to take the data and transfer it back to main memory, which here is the disk represented by the sloths. Similarly, if I need to retrieve that data back, the CPU has to go to the disk and read or load that data for the user to access and then do computations with. Fortunately, getting stuff and storing stuff from the disk is very, very slow, like orders of magnitude slower than the CPU. And this gap has only widened in recent years as CPU access time has improved faster than the disk access time. And this is called the memory wall, or the von Neumann bottleneck. So, how do we tackle this problem?
Well, first we're going to have to investigate what kind of data we typically pull and store in disk at any given moment. Look at the above C program, which is really just calculating the sum of all of the elements in an array A that has length n. Do you notice anything? I notice that every single iteration of this loop references this variable sum. That is, once sum is accessed for the first time, there's a high likelihood that we're going to be using it again and again and again in the near future. I also notice that once we access, say, the third element of the array, on the next iteration we need the fourth, and then the fifth. And since arrays are stored as contiguous blocks of memory, this means that even though we're not referencing the exact same memory location every iteration, we are accessing things that are very, very close to each other. And this is a key principle of memory known as locality. So what this means is that even though disk memory is a giant block of bytes, at any given time, we're probably only working with this tiny little subset of memory that all happens to be clustered together.
So because of locality, we can actually just take that small set of data we know we're going to use again and again and bring it as close to the CPU as possible, so the chip doesn't actually have to go all the way back to main memory every time it needs to access something. This idea is called caching. Typically, there's an inherent trade-off between speed and space on a computer system. Faster storage must be smaller and more expensive. But caching gives us the illusion of fast, big data because we've created this large pool of storage at the bottom, but the program will typically only interact with the fast storage at the top. And actually, we can iterate this idea a bunch of times.
Instead of just having one cache, we can have multiple cache. We can have a cache that leads to a slightly larger cache, and that leads to a slightly larger cache, all the way back to disk. And this creates a memory mountain that looks like this. So now, if I want to access a data value, I can go to main memory and pull it and all of its surrounding data all the way up to the top layer of the cache. And now, whenever I might need that value or any of its neighboring values in the future, it's right there for easy access. So I'll only need to interact with the disk again when I need memory that's stored pretty far away from the original data value, which doesn't happen that often. Because of locality, in the real world, the miss rate of these caches is typically only around 1 to 3%. And that's a good thing too, because the smallest and fastest caches have very, very good latency, like basically zero, especially when you're comparing to something like a disk that can take up to 10 million cycles.
As it turns out, von Neumann can rest easy. With locality to the rescue, we can work around performance bottlenecks to deliver the memory and speed that you're used to.